So far, we've thought about measurements as ranges on a number line or a scale corresponding to a phenomenon of interest where the increment on the scale corresponds to the unit that we're using. So for example, we were looking at this length or distance measurement of 32.813 centimeters that was on a centimeter scale, and there was a range to that because there's some uncertainty in that value, plus or minus 0.002, if I remember right. Now, the size of the increment can vary, right, and can have any possible value. And this means that there are an infinite number of possible units that we can use to express a measurement in any given phenomenon, because the increment size can vary. And we often want to change the size of that increment to convert from one unit to another, maybe to make the value a little more human-friendly or express some measured quantity in units that we can directly compare to some other measurement or something along these lines. And the process of going from a measurement in one set of units to the same measurement in another set of units is known as unit conversion. And conceptually, all we're doing here, graphically speaking, is just stretching or shrinking this number line to change the size of the increment. So for example here, I have our old scale, our old centimeter scale, where you can see the increment going from 32.80 to 32.81, 32.82, 32.83. And I have our old measurement as the blue rectangle here. I've also overlaid on this a red number line where the red increments here are in units of 0.01 inches. So actually off to the left here, you can't even see it, is 12.91. Here's 12.92 inches, here's 12.93 inches. And essentially notice what we've done relative to the centimeter increment is we've stretched it out. An inch is about 2.5 centimeters. And so the increment for an inch is about 2.5 times as big as the increment for 1 centimeter. But we can still express this measurement in units of inches. It turns out to be 12.919 inches, plus or minus 0.0008. We can also express the uncertainty in units of inches. And essentially what we did was just stretch out the size of the increment, taking it from 1 centimeter to 1 inch. To mathematically convert from one unit to another, we have to make use of what are called conversion factors. All a conversion factor is a ratio of the size of the increment of one unit to the size of the increment of another unit associated with the same phenomenon. And actually that last bit is important. If you're looking at a quantity that has units that are a ratio of two other units, and those units don't refer to the same phenomenon, that actually gives you physical information. So something like a speed, meters per second, is not a conversion factor. That is an actual physical quantity that gives you interesting physical insight into some situation, right? We'll see this throughout chemistry, that there are units like grams per mole or liters per mole or kilojoules per mole that are not conversion factors but nonetheless use ratios of units. Conversion factors specifically refer to the same phenomenon. So for example, we can generate a conversion factor by expressing, for example, how many inches there are in a centimeter. Inches per centimeter both refer to the fundamental phenomenon of length. They just use different increments. We can also take conversion factors involving units and raise them to powers to create new factors. And this is commonly done when we're converting between area or volume units, for example. So say we have a volume of 3.26 cubic meters, and we want to express that measurement in terms of cubic feet. And all we know is that 1 meter is equivalent to 3.28 feet. We're interested in cubic meters and cubic feet, so it may seem like we're missing information here. But what we can do is start with this conversion factor of 3.28 feet for every 1 meter, and just cube it, raise everything to the third power, to generate a new conversion factor that's going to be feet cubed per meter cubed. And we can multiply that then by our known volume in meters cubed, and this comes out to 35.3 feet cubed per meter cubed. Multiply that by our known volume in cubic meters, 3.26 meters cubed. The meters cubed divide out. I've got meters cubed in the numerator here and denominator here, and we end up with 115 feet cubed, which is right about where we would expect this on intuition, right? A foot is a lot shorter than a meter, so a foot cubed is much smaller than a meter cubed, and so 3.26 meters cubed is going to correspond to a much bigger number of feet cubed, in this case 115. If we want to convert between two units that differ only in a metric prefix like millimeters and centimeters, we can do this by thinking about the two units relative to a standard and simple quantity like 1 meter and set up a ratio of 1 meter in millimeter units and 1 meter in centimeter units using our knowledge of metric prefixes. So for example, to build this conversion factor of centimeters to millimeters, I can say, well, the ratio of 1 meter to 1 meter is of course just 1, and this is how I'm going to build out the conversion factor. And from the metric prefixes, I know that there are 10 to the third millimeters in a meter and 10 to the second centimeters in a meter. So I can set up this conversion factor to make this unit conversion from centimeters to millimeters. And of course, the meters, if you think about this, are sort of extraneous. This could be any unit. It doesn't have to be meters, could be absolutely anything. And we can say that 10 to the third milli anything is equivalent to 10 to the second centi anything. So this metric unit conversion generalizes to absolutely any unit. This is usually done to bring the measurement's value into human-friendly territory. But just to give a simple example of this, say we had a measurement that was 2 centimeters and I wanted to express that measurement in units of millimeters. I can use this conversion factor that we just built out, multiplying the 2 centimeters by 10 to the third millimeters for every 10 to the 2 centimeters, and the centimeters would divide out, and I would end up with 20 millimeters. Another example of this that's a little bit more stark is shown at the bottom of the slide. The mole, which we'll talk about later in the course, is a very large counting unit. For example, 1 gram of the drug rapamycin corresponds to only 0.00109 moles of the substance. Very tiny value, right? And so we want to express this amount in units that have a tiny increment, like millimoles and micromoles. And to get started, and notice this is just a change in metric prefix. We go from no prefix to either the milli or the micro prefix. So we can use our knowledge of metric prefixes to set up conversion factors here, asking questions like, how many millimoles are there in 1 mole? Well, based on the definition of the metric prefix as 10 to the negative 3 power, there are 10 to the third power millimoles in 1 mole. And when you multiply through, that gets us to 1.09 millimoles is equivalent to 0.00109 moles. Similarly, for micromoles, the definition of the metric prefix tells me that there are 10 to the 6th micromoles in a mole. So I can use this ratio to go from moles to micromoles. After I multiply everything out, we end up with 1,090 micromoles is equivalent to 0.00109 moles. Now, before I leave this slide, a point I want to make is all 3 of these measurements are equivalent to the same measurement, really, right? They all express the same fundamental measurement, 0.00109 moles. It's just the size of the increment on our number line is different in each case. And so the values vary and the metric prefixes vary. But these are really all representations, equivalent on some level, representations of the same measurement of the same phenomenon in the same system. The one unit conversion that is not a scaling of the increment that's a little bit weird is the one between the Celsius and Kelvin temperature scales. And actually, Celsius to Fahrenheit is even weirder. We'll look at that on the bottom half of the slide. But Celsius to Kelvin or Kelvin to Celsius is actually just a shifting of the scale. The Kelvin scale came about essentially when we realized that negative 273.15 degrees Celsius is the lowest possible temperature that is achievable. And so we shifted the Celsius scale so that negative 273.15 corresponded to 0 in a new unit that was then called the Kelvin. And so to find a temperature in Kelvin from a temperature in degrees Celsius, we add 273.15 to the temperature in degrees Celsius. So for example, negative 273.15 degrees Celsius corresponds to 0 Kelvin. The Fahrenheit scale is both shifted and uses a different increment. And so the conversions here, which I won't go through in detail, I just kind of present them as yet another wacky example of unit conversion involving temperature. The increment is scaled by 5/9. The increment for the Fahrenheit scale is smaller than the increment for the Celsius scale. You may be familiar with this if you've ever lived abroad. Temperatures in Celsius are generally lower, smaller numbers. The values are smaller than on the Fahrenheit scale. And the reason is the increment is larger for Celsius than it is for Fahrenheit. And then we're going to either subtract 32 or add 32, since Celsius defines the freezing point of water, right, as 0 degrees Celsius. So these are wacky unit conversions that use this shifting or translation of the scale. This is not common, and really temperature is the only context in which you'll see this. Metric prefixes are a great way to embed very large or very small powers of 10 into the expression of a measurement. Another way we do this that's a little bit more explicit, a little bit more clear, doesn't require you to memorize metric prefixes, is called scientific notation. And scientific notation, the value of a measurement is expressed as a product of a power of 10 and a number between 1 and 10. This number between 1 and 10 has a special name. It's called the significand. We'll see where that comes from later when we talk about significant digits. And the power of 10 is raised to some number, which is called the exponent for pretty obvious reasons. This is the exponent on 10. Other than that, scientific notation, really it just refers to the value. The units are exactly as we would expect. There's nothing special there. Scientific notation is generally used for very large or very small values. Doesn't have to be, but this exponent is usually a relatively large integer in magnitude, right? 10 to the negative 9 or 10 to the positive 8, 10 to the positive 12, something like this. When we multiply or divide values in scientific notation, this is relatively straightforward. We just divide or multiply or divide the significands and then adjust the exponent based on rules for multiplying or dividing exponents, right? Where we would, if they were multiplied, the powers of 10 were multiplied, we would add the exponents. If they were divided, we would subtract the exponents. And just as a third note here, the significand may be negative. It is possible for measured quantities to be negative, and so the significand can have a negative value. To go from kind of the standard notation to scientific notation, I wanted to work this example with the moon's distance from the Earth. Now, if my eyes don't deceive me, this corresponds to 394,000 kilometers from the Earth, and we want to express this in scientific notation. The way to figure out the power of 10 is to lay down the decimal point, I'm going to zoom in here briefly to show this, where it's located, and then count the number of steps we need to take to get just before, just to the right of the leftmost number. So 1, 2, 3, 4, 5 steps were required to go from the initial point on the initial decimal place to where we want it to be in the scientific notation. And so the exponent here will be 5, and I can go ahead and write something times 10 to the 5th kilometers. And the something is the number we get by placing the decimal point just to the right of that leftmost number, 3.94000. And I do encourage you to include the trailing zeros. We might return to this later in discussions of significant digits, but if those zeros are included in the way the measurement is expressed, they're often thought to be significant. Probably not in this case, since the moon is probably not exactly 394,000 kilometers from Earth, so maybe we should remove those zeros. But more often than not, we'll include even trailing zeros when you write out scientific notation like this. Let's do one more example of this involving a very, very tiny value. And we're going to make use of this process at the top of the slide, which we've already done, but I forgot I had on this slide. And so We'll see how this works a little bit more systematically in the case of this very, 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 very tiny length value, 0.000062, if my eyes don't deceive me. Okay, so we want to express this in scientific notation. The first thing we do is place a decimal point to the right of the leftmost non-zero digit. Here that's a 6. Let me zoom in. And so we're going to place a decimal point right here. And this actually tells me straight away that the significand here is 6.2. So we're going to have 6.2 times 10 to some power, 10 to the exponent. Now, what we're going to do is count the number of steps it takes to get from this new decimal point to the standard location of the decimal point between the ones and tenths place. 1, 2, 3, 4, 5, 6, 7. 7. And I was walking to the left, so the exponent here is going to be negative, and it will be -7 since we took 7 steps to the left. Another process that I'll often employ informally is to count out starting from the left and moving to the right until I hit the first non-zero digit and go, okay, 10 to the -1, 10 to the -2, -3, -4, -5, -6, -7 is when I hit the 6, and so the exponent here is -7, and then we don't want to forget to include the units of meters here. We're going to discard any leading zeros after this point. We have a 0 here, but we discard this. Any leading zeros are not going to show up in the number in scientific notation.